Good afternoon. We're delighted to have Krishnath Riya here. Almost 45 years ago, he wrote the Bible on branching processes that even though there's a lot of further work on the topic, it still looks a state of the art today. In many results were just optimal, so there's nothing better to do. And yet he's continued and had lots of impact on the area later. In particular, he'll tell us something about branching processes today. Please.
Thank you. Thank you all for asking me to speak here. This is really nice. I want to talk about a problem called coalescence. And I will talk about coalescence in branching trees. So here is the very simple version of the problem. Take a binary tree. So a rooted binary tree, that is. So you start with one vertex at time 0, splits into exactly 2 vertices, and that in turn splits into 2, and so on. So you notice that at level 0, there is exactly 1 vertex. At level 1, there are 2. And at level 2, there are 4, 2 squared, and so on. And you can guess that at level n, there's going to be 2 to the n vertices. So now, supposing you choose 2 vertices from level n by what is known as simple random sampling without replacement, which means there are 2 to the n vertices available. There are 2 to the n choose 2 pairs that you can choose, and you choose one of those pairs with equal probability. Supposing you choose, say, 2 vertices, and now you trace their lines back until they meet. Call that generation where the lines meet x sub n. So then trace their lines back, in time till they meet. Say at generation x, at level xn. Clearly, they will meet at the origin, but they could be much before that. So the question is, xn is going to be a random variable. The tree itself is deterministic, but I've injected randomness by my sampling procedure. So the question that we want to ask is, what is the distribution of xn? One. And 2, what happens to this as n goes to infinity? So these are 2 questions that we want to ask. And this is actually very easy to answer in the following sense. You notice that the following probability calculation is very easy. If xn is going to be anywhere from 0, 1, 2, 3 up to n minus 1. I'm looking at the nth generation. So the meeting place must be at least n minus 1 and all the way down to 0. But if I want it to be less than k, then at level k, I have 2 to the n vertices. Each of these individuals have a time n minus k left to them. So they would have 2 to the n minus k descendants by time n. So if I want xn to be less than k, that event happens with, I have 2 to the power k vertices, and I choose 2 of these guys, and then look at their descendants, and then I want to choose 1 from each of these things. So that are 2 to the n minus k times 2 to the n minus k. So these are the number of favorable ways of producing xn less than k, divided by the total number of choices, which is 2n choose 2. So this is the exact probability for k equal to 1, 2, all the way up to n. Now you can choose, this is indeed equal to 2 to the k times 2 to the k minus 1 over 2 times 2 to the n minus k, 2 to the n minus k. And the same 2, the denominator is going to be 2 to the n times 2 to the n minus 1 over 2. And that 2 will cancel with the numerator 1. And
so xn less than k, so
xn is less than k.
You wanted to first choose the common.
So what I do is I go to level k. There are 2 to the k vertices, and I choose 2 of those guys, and I look at the number of descendants at time n minus k, at time future time n, which is n minus k. So that's what this calculation is. But this is equal to, I can pull out the 2 to the k from here, so it's 1 minus 2 to the minus k. And then pull out the 2 to the n from here, which is 1 minus 2 to the minus n. And then I have 2 to the k times 2 to the k, 2 to the 2k, 2 to the 2k cancels, 2 to the 2n, 2 to the 2n, all of that cancels. So this is the exact probability, and this converges as n goes to infinity to 1 minus 2 to the minus k. So we have shown that x sub n has an exact distribution which is approximately geometric, and in the limit it is a geometric random variable. Now clearly what we did for the case of binary tree can be done for any binary tree where, or emery tree where its tree is deterministic. Well, since I have worked in branching processes, as he said, for a long time, so a natural question is, what happens if the tree is not deterministic, is a purely random tree? So the question that we want to ask is, so this is, what if the tree that you have, the rooted tree that you have, is a Galton Watson, or if I were to be honest with Australians, BGWBP, BNMA Galton Watson branching process, and is a tree. Now you remember how that is generated. So you are given the following: a probability distribution Pj, j greater than or equal to 0, Pj non-negative, and then summation Pj equal to 1. Then you generate, so this is 1, 2, generate a doubly indexed family of random variables, j greater than or equal to 1, n equal to 0, 1 to infinity, of IID random variables with distribution Pj. Then you define the population size in the n plus first generation to be the number of children born to the individuals in the nth generation. So if there are Zn individuals in the nth generation, each one of them produces children according to this process, and then Cnj is the number of children born to the jth parent in the nth generation. And this works if Zn is positive. If Zn is 0, the population is already gone, there is nobody to produce anything, so it will stay at 0. Oh, sorry. So 0 is what is called an absorbing barrier. Once you hit 0, you are stuck at 0. Otherwise, you can go this. So then the following result is a well-known theorem. Goes back to Galton himself, and then Reverend Watson, who produced a wrong solution, is that the probability Zn equal to 0 for some n greater than or equal to 1, conditioned on Z not equal to 1, is equal to 1 if the mean number of children produced per parent is less than or equal to 1. And is strictly less than 1 if this m is greater than 1. So that's a very well-known result, namely the mean number of children produced has a role to play in the tree surviving for indefinite time or terminating in a finite time. So there are many more results, and here is the classification. M is the mean, that quantity there. M greater than 1 is called 1 less than m less than infinity. That's called supercritical. M equal to 1 is called critical. And m less than 1 is called subcritical. And I'm going to discuss one more case which has not been discussed in my book and or any other book for the model. It's called m equal to infinity case, explosive case. I'll talk about that as well. All right, so now let me describe the results for these cases which have been well studied in the literature first. So if you take a supercritical branching process, and let's assume that there is no extinction, that is P naught is 0. So here is the first result that we can state. So theorem 1, let P naught be 0, no extinction, and let the mean number of children born to one parent be finite. So then, well, I'm picking only 2 individuals at random from the nth generation. The nth generation is not going to be dead. It's going to be growing very rapidly. Then the probability, I'm going to call the coalescence time xn2. That's the generation number when these 2 randomly chosen individuals meet, their lines meet, xn2 is less than k, conditioned on the tree itself. So in other words, remember there are 2 sources of randomness. The tree itself is randomly generated, and then I'm injecting randomness by sampling. But suppose the tree is generated in the next room and you bring the tree here, and then you do the sampling on the vertices. That is what this conditioning means. Given the tree, you look at this quantity, limit as n goes to infinity of this exists, and it's a function of k and t, the tree, for k equal to 1 to infinity, exists. And what is more, for almost all trees, this is a proper distribution. And pi k of t converges to 1 as k goes to infinity. So in particular, the limit distribution exists for xn2. It's going to depend on the tree. And of course, by the bounded convergence theorem, the unconditional average also exists. So this implies in turn that the probability that xn2 is less than k without the tree averaging over all tree also exists, because this is bounded by 1, and so taking the expected value is okay, will converge to pi k, which is equal to expected value of pi k of t. Now, so this is theorem 1. When m is finite but greater than 1. So this is the supercritical case. And if I have time, I will indicate the proof for you. Then let's look at the critical case. Here is a problem. In the critical case, we know that the tree is going to die out with probability 1. But then I want to do some sampling. So I'm a mathematician, so I will assume that the tree is not dead. So I'm conditioning on an event where the event probability is actually going down to 0. I'm not the first one to do this. Kolmogorov already did this. Kolmogorov did this way back in the late or early 40s. So the critical case is this is m equal to 1. And of course, m equal to 1 is a possibility with p1 equal to 1. But that's a purely deterministic tree. Everybody produces exactly one child. and we want to rule that out. If we rule that out and say, let's assume P1 is less than 1. If P1 is 1, there is no extinction. The same, everybody produces one child and so on and so forth. Okay. In this case, what is your intuition? Xn 2, well, we have to condition on the fact that at time n, the population is not extinct, number 1. Number 2, it has at least 2 individuals. Well, fortunately for us, Kolmogorov had proved a very beautiful result long ago, and that is the following. It requires the finite second moment hypothesis. So let me quote that result for you. So m equal to 1, and then P1 is less than 1. And supposing you assume that the finite second moment exists. So assume all of these 3 conditions. So given. If all these conditions hold, then the survival probability is going to die like 1 over n, and the population size is going to be of the order n. Then 1, the probability Zn is positive, that is, the process is not extinct. We know that that probability has to go to 0, but n times that converges to sigma square over 2 as n goes to infinity. This is something that Kolmogorov had established, number 1. Number 2, the probability that Zn over n is less than x conditioned on non-extinction. If the process is not extinct, how big is the population? Roughly speaking, of order n, which is distinctly different from the supercritical case where the population explodes at a geometric rate. It turns out that this converges to 1 minus e to the minus 2 over sigma squared x. For any x positive, so he proved this result. So,
The second one is Yaglom's limit law.
yeah, Yaglom was his student. It was not. There is also a subcritical result which is attributed to Yaglom. So we did some research, and then eventually we attributed to Kolmogorov. But you are right. There's the name of well, again there are 2 Yagloms.
Right.
So we have to be IM Yaglom and the AM Yaglom, which one, we have to. So I just thought I'll Kolmogorov on his students, let us say. So then it turns out that in the critical, there is one more result that we need, which was not proved by Kolmogorov, but which I proved just a few years ago, and that is the following. Here is time 0, and here is time n. Supposing at time n the population is not extinct, condition on the event, that's an event of a very small probability. Then go to level k. The population is not extinct by time n, therefore it cannot be extinct at time k. But then there are a large number of individuals at that time, say zk, and look at the lines initiated by each one of them. Each one of them has a certain number of individuals left, but some of the lines could be dead, some of the lines are not dead. So now look at the following process. V sub n is going to be, you look at Zn minus k super k comma I divided by n minus k times the indicator function of Zn minus k I super k positive for all those, for I equal to 1 to Z sub k. In other words, I go to level k, there are zk individuals, each of them initiates a line of descent, and then look at what happens to their population size in each one of them, divide that by n minus k, and look at only those lines for which the population is not extinct by time n. So now this is a collection of points on the non-negative half line. It has a random collection of points. So it's what is called a point process. Question, what is happening to this point process? And I showed that this point process, so this is blah, blah, blah. You can put my name on it if you like. 3, Vn conditioned on Zn greater than or equal to 2, or Zn not equal to 0, if that's good enough too. This is a point process. So you have to go to the space of point processes and talk about V convergence in the space of point processes. You can use a Laplace functional, blah, 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 and so on. So
fixing k, or k also is very...
No, yeah, that's a good point. K has to go to infinity, and n has to go to infinity. So let me write it down. Let n go to infinity, k go to infinity, such that k over n goes to u, where u is between 0 and 1. So it has to be roughly of the same order as n. Okay, supposing that happens, then, so this is the third result, then Vn conditioned on Zn being non-zero converges in distribution to a random point process where the number of individuals, so it's going to converge to, remember this is a non-negative quantity, a whole bunch of non-negative quantities, and this will converge to the following. It's going to be converged to eta 1, so eta 2, eta, say, a random variable v, where the etas are going to be exponential distributed, and v is going to have a certain well-defined distribution coming from here. So let me write down that precise result. Because this is a very useful result that it comes up in another context also in it's not in this paper, it is in this paper. Yeah. I don't remember where it is. Ah, there it is. It converges to a point process eta 1, eta 2, eta n sub u, where the eta i's are independent random variables, exponentially distributed. N sub u is geometric with parameter u. So you generate a sequence of IID the exponential random variables, and then generate an independent geometric random variable with parameter u, call that n sub u, then go fix only these random variables. So this is going to be a random point process on the non-negative half line. That's what this will converge to. So it's not easy to prove that result, but it requires a Laplace functional, and then this book of this Norwegian mathematician who is at Auburn. What is his name? I keep forgetting. I will give the reference, precise reference. Kallenberg. Kallenberg has a very nice method called Laplace functional method to prove this. So you have to use that to do that. So here xn2, so in this case, you look at xn2. xn2 is the conditioned on non-extinction. The population is not extinct. Now xn2, you take two individuals at random in the nth generation, trace their lines back, and see when they meet. And the question is, what is happening to xn2? Now notice, in the supercritical case, xn2 is way back in time. Here it is not way back in time. xn2 is roughly of the order n. It's less than u, converges to a function h of u. And this h of u, h of 0 plus is 1, h of 1 minus is 1, h is absolutely continuous on 0, 1. So there is a proper distribution function such that xn2 over n converges to that.
H of 0 plus is 1.
Well, xn2 has to be between 0 and 1. So in other words, the random variable that it goes to is in the open interval 0 to 1.
Yeah, but H of 0 plus is 0.
It is 0, 0, 0, sorry. Not 1, of course. Thank you. H of 0 plus is 0. I meant 0. So the H is a distribution that is sitting on the open interval 0 to 1. It's an honest distribution. It is a non-trivial distribution. So the coalescence takes place somewhere in the middle of that interval. It's neither close to the present nor close to the past.
Can you write down what H is?
Yes, I can write down. But, well, you asked for it, so I'll write it down. It's a fairly complicated thing. It is going to involve this random variable. So H of u is going to be equal to 1 minus expectation of phi of nu. Now, nu, remember, is going to be a geometric random variable with parameter u. And then, so our phi of j is going to involve expectation of summation 1 to j eta I squared over summation 1 to j eta I whole squared, where eta 1, eta 2, eta j are IID exponential 1 random variables. So the formula for H is not very simple. It's a little bit, it comes from this point process idea. Now notice that this quantity, this is an interesting problem in itself. If you take IID random variables, xi be IID, so this is a problem.
Use a different pen. This one is. Maybe you want to use a different pen. That pen is too.
All right, okay. So I have the cover here. So here is an interesting problem. Let xi be IID random variables, say positive random variables. Then if you look at 1 to n xi squared, the numerator, denominator is 1 to n xi quantity squared. The behavior of this sequence was studied by a number of people in Bell Labs, for example, long ago. And notice that if the mean of, if the random variables of a finite second moment, the numerator is going to be like n, the denominator is going to be like n squared, so this whole thing will go to 0. But if xi's have heavy tails, if xi is, suppose in the domain of attraction of a stable law of order alpha less than 1, then these two guys are going to be roughly of the same order of magnitude. And so they will not go to 0. But that kind of a thing comes up here, but then here there's no problem. Because eta i's are going to be IID, eta I are IID exponential 1 random variables. So everything is going to be okay here. This is going to be dying at the most, at the rate like 1 over j, and that's enough to make this thing proper. So in the supercritical case, coalescence takes place way back in time. In the critical case, coalescence takes place neither close to the event in the infinite past or the present, somewhere in the middle. And it turns out that in the so-called subcritical case, the subcritical case is the following, where m is less than 1. So theorem 3, subcritical. Here m is less than 1. Remember what m is? M is the mean number of children produced per parent. And if it is less than 1, the population is dies out. So the question is, again you have to condition. So it turns out, so that is m is less than 1. So theorem, then the probability xn2, n minus xn2 is less than k, conditioned on Zn positive. So the coalescence is very close to the present. It is not way back in time. Remember, in the subcritical case, the number of individuals alive at time n is going to be a proper random variable. So this converges to pi k, and for every k, 1 less than or equal to k less than infinity, and then pi k goes to 1 as k goes to infinity. So to summarize, we have the following situation so far. If the mean is greater than 1 and the population is not extinct, coalescence is going to be way back in time. If the mean is 1 and the population is not extinct, then the coalescence is going to be somewhere in the middle, so roughly of the order n times u, where u is somewhere between 0 and 1. And if m is less than 1, the coalescence is going to be very close to the present. So now I want to consider one more case, and that is the explosive case. And then I would like to apply these arguments to what are called branching random walks. So explosive case. Explosive case is when m is infinity. When each person produces number of children, random number of children, whose mean is infinity. But then it turns out that I need one more hypothesis, the probability. So this is in addition, I have to assume that summation pj j greater than x. This is the so-called tail probability. And it's going to go to 0 as x goes to infinity. But I want it to go to 0 reasonably slowly. This is equal to x to the power minus alpha times a slowly varying function. That means what? L of cx over L of x goes to 1 as x goes to infinity for every 0 less than c less than infinity. Like log x would be slowly varying, but any power of x will not be slowly varying. Square root of x will not be slowly varying as x goes to infinity. And with alpha between 0 and 1. So that's my hypothesis about the distribution of Pj. If this is so, then the probability that the coalescence now, and again I'm assuming P0 is 0, so there is no extinction at all possible. And in this case, again, the coalescence is very close to the present. Xn less than k converges to pi k as k goes to infinity. In other words, in the rapidly growing population, coalescence takes place very close to the present. In reasonably growing population, coalescence takes place very close to the beginning. In a critical case, it's somewhere in the middle. In the subcritical case also, it's close to the beginning. Now, in the explosive case, something interesting happens also. So here is a side result. This is due to P.L. Davis, a Dutch mathematician, and then David Gray, an English mathematician, and that's the following. So assume m is infinity, and Pj belongs to the domain of attraction of a stable law of order alpha, namely this condition. This is a necessary and sufficient condition for Pj to be in the domain of attraction of a stable law, proved by Feller. If this is the case, then you take two individuals, have them produce branching independently of each other. Then one of them will wipe out the other. So it is as follows. Namely, if you look at the population size at the n plus first generation, that is equal to summation c and j equal to 1 to z sub n. The population is made up of the individuals produced by the people in the nth generation. Now, these random variables are all independent, identically distributed, conditionally independent of Zn. So you divide by 1 over Zn to the power 1 over alpha and multiply it by Zn to the power 1 over alpha. So take logs on both sides. Log Zn plus 1 is called this quantity, say V sub n for the moment, is equal to log Vn plus 1 over alpha log Zn. So that in turn suggests that alpha to the power, again, I keep it outside. Alpha to the power n plus 1 times log Zn will be equal to alpha to the power n plus 1 times log Vn plus alpha to the power n times log Zn. Zn plus 1 here and log Zn. And I can go down the line, and then it essentially sort of form alpha to the j plus 1 log bj, j equal to say 0 to n. So this would suggest, remember alpha is less than 1, alpha to the j is a geometric sequence, summation alpha to the j converges, vj's are identically, well, will converge in distribution to something. So it takes some more work to show that this quantity converges, and if that is so, so this is a theorem now. Let me write down as a theorem, and here is an indication of the proof, but it's not really a proof yet. So theorem, let pj, let m be equal to infinity, and summation pj, j greater than x, be asymptotic to x to the power minus alpha times L of x, L slowly varying at infinity, alpha between 0 and 1. If that is the case, then alpha to the power n times log Zn converges to a random variable, say u, with probability 1, and the probability that u equal to 0 is 0. U is a continuous random variable, which says basically, if you think like on an intuitive basis, alpha to the n times log Zn is approximately like u. If that is the case, log Zn is approximately like 1 over alpha to the power n times u. Alpha is less than 1, 1 over alpha is bigger than 1, call it rho, equal to rho to the power n times u. If that is the case, the population size Zn is like e to the u times rho to the n. That means the population grows, unlike the Malthusian rate of growth, it is super exponential. And well, we know the offspring distribution doesn't have a finite mean, so this is not that much of a surprise. But here is the interesting thing. Supposing you start one line of descent, and I start one line of descent, both with the same distributions. Then Zn super 1 is going to be like e to the u1 times rho to the power n. Zn super 2 is going to be like e to the u2 times rho to the power n. u1 has a continuous distribution. So u1 cannot be equal to u2, which means if I were to take the ratio of these two guys, it's going to be u1 minus u2 times rho to the power n. It will either go to plus infinity or go to 0. So one will wipe out the other. So which may explain the fact why the coalescence is very close to the present. If you take two individuals, very likely they are coming from the same ancestor. That's not a proof. That's an economist proof, not a mathematician's proof. But that's roughly what the idea is. So now, I've described some basic results for what's called coalescence. Coalescence in this case is the problem of generations that are meeting, okay, after some time. Now I want to give an application of some of this, so you can see where to go in a number of directions. You can think about what happens to a continuous time process, what happens to two-type branching processes, multi-type branching processes, and so on. Lots of things. So if you have good students, put them on. But I want to go in a slightly different direction, and I want to talk about what's called branching random walks. This is the problem. I kept it outside for too long. I keep on writing. Okay. Branching random walks. So what is a branching random walk? Well, it's a branching process plus a random walk imposed on it. So you start with an ancestor at time 0, and then this ancestor has a random number of children, and this ancestor is located at some site x. x0 is the location of this ancestor. But these children essentially migrate from where the parent stays and go to a new place. So they go to x0 plus x1, 1, x0 plus x1, 2, and then x0 plus x1, c1, the number of children born to this parent. Okay? And then the children of these children do the same thing. They migrate from where the parent lives to a new place and so on. So if you look at zeta n is the actual position of all the individuals in the nth generation, xn1, xn2, xn, zn. So this is the position, the point process generated by the positions of the zn individuals in the nth generation. Question, what is going to happen to this? In particular, we know, well, this question makes sense only with, let's assume that P naught is 0 and 1 is less than m less than infinity for the moment. Consider that case. And now, what will happen to this point process as n goes to infinity? There is two sources of randomness. The tree itself is random, and then the jumping is also random. So we need to make some assumptions about the jump distribution, and I've already mentioned my assumptions about the tree structure. So let P naught be 0. Let x11, x12, x1 c1, this random vector. Well, supposing I make a simple assumption that they are all identically distributed with mean 0 and then finite variance. So that's not such as, well, we are essentially, otherwise you'll have to subtract of the mean, and an expectation of x11 squared equal to sigma squared is finite. So now the question is, what is going to happen to the empirical distribution? What is the distribution that I'm looking at? 1 over n summation indicator function of xn I less than or equal to x, I equal to 1 to zn, or 1 over zn. That's what I'm looking at. The proportion of individuals which are to the left of x. But I roughly know, well, okay, so here is the idea of analyzing this thing. You have a large number of individuals located all over the place, and you want to know what is going to happen to the empirical distribution of the points on the real line or whatever space that you are in. Now notice, if I pick two individuals at random from this collection and trace their lines back, they're going to be way back in time, which means that they have a lot of time to evolve independently. That means their positions are going to be like an ordinary random walk, and they are independent as well. And therefore, you would look at the empirical distribution, namely this particular quantity. So this is a theorem. Under this hypothesis, if you look at number of individuals who are to the left of, say, sigma times square root of y, sigma times y times square root of n, divided by the total number of individuals. This is the total number of individuals. This is the proportion of individuals whose children, or the number in the nth generation, who are located to the left of sigma times y times square root of n. Not surprisingly, this will converge to the standard normal distribution function in probability as well as in mean square. And the reason for this is that if I take two individuals at random and trace their lines back, they're going to meet way back in time. So essentially, their lines are independently developing.
This also holds almost surely.
Well, yeah, that is a little bit harder, but yeah, it's almost surely true. So this is one result. And now, you can also, there are some variations of this. If you don't want to assume finite second moment, but if you assume that these displacements are in the domain of attraction of a stable law, there will be a corresponding version of that, but I will not go into that. So one last result that I want to state is that is what happens in the explosive case. So again, take the branching random walk. P naught is 0, m is infinity, and summation pj belongs to the domain of attraction of a stable of order alpha, 0 less than alpha less than 1. In this case, notice what is happening. If you take two individuals at random from this collection, then their lines of descent are going to meet much sooner, very close to the present. So they have a lot of portions that are common. and then there's a small portion which is not common. And that's going to get wiped out by the denominator. So what happens is this. In this case, this is a theorem. Assume again that the expectation of x11 is 0, expectation of x11 squared is equal to sigma squared is finite. Then, if you look at the number of individuals to the left of sigma y times square root of n and divide that by n, Zn, consider this stochastic process y, so indexed by the parameter y over the whole real line. For each fixed y, this converges to a random variable. So this is converging to, I want to claim this delta y minus infinity less than y less than infinity, where delta y is going to be the indicator function of a standard normal random variable less than or equal to y, where n is n01. And then here I have to, I deliberately left, in what sense do I mean by this? Well, this is a family of random variables indexed by minus infinity to plus infinity y. This converges to this for every finite collection y1, y2, yk. But then these processes live in the Skorohart space minus infinity plus infinity. So it would be nice to prove that this converges to take place in the Skorohart topology as well. But finite dimensional convergence plus tightness is required. I have not been able to prove tightness yet, but I've been able to prove the finite dimensional convergence. So this converges in distribution to this delta y, where delta y is, you go to the next room, generate a standard normal random variable, bring it here, and then construct the trajectory. Notice that if I give you the value n, the trajectory is going to be 0 for a long time, and then jump up, and then it's going to stay at 1. So I have proved this result, that namely for finite number of coordinates y1, y2, yk, the convergence distribution takes place. But I would like to prove that this is tight as well, which I have not been able to prove.
This is the number of particles that have moved less than sigma y root n, and you have this explosive.
Yeah. So you remember the coalescence takes place very close to the percent. That means yeah. So this is the super
close to the coalescence happened close to the
present. That means that much of the trajectories have much of the things have a lot of things in common. Only the last bit is going to be different. All right. So let me see. What time do I have? 4:20. I'm supposed to stop now, right?
I mean, you can take a
Yeah. Well,
a few more minutes.
okay. So let me. Where is the original paper? Right here. Yeah. Then there are many directions you can go to. For example, one direction would be what happens in the two-type case or the multi-type case. In the multi-type case, you choose the two individuals at random from the nth level. They could belong to two different types, and their ancestor could be in yet another type. What would happen to these things? And then you can talk about what if individuals live a random length of time. In other words, continuous time branching processes. And then there is a process that my another Atreya, my brother's son, he's a probabilist as well, also in the Indian Statistical Institute in Bangalore. And one Shrikant Iyer, we worked on it, and we considered the following problem. You have a branching process, and each individual has a certain random length of life. And during their lifetime, they move according to a Markov process. So this is a branching random walk, but branching Markov process, as it were. And then again, you look at the distribution of the point process generated, and there are some results. And there that paper was written long before I did this work on coalescence. So we have only results with the finite mean, but the infinite mean case is open. I mean, a number of problems are open. I have listed a whole bunch of open problems in a paper that I wrote for a conference in Spain about 6 months ago. So I can describe them to you. But there I will stop.
Thank you very much. So these papers, you
Yes.
upload the papers on the archive? Or where can we
I
find
don't know
them?
how to do that, but it is.
On your webpage, or where can we find them?
Yeah, my son was able to find all of them there. I told him that he did something and then out showed up all these papers. But I don't know how to do them myself. But he may. Do you have copies of all my papers or no? Not yet.
Anyway, we can, if
Yeah,
they're,
you can download them.
if
So.
they're findable online, we can find them.
Yeah, actually, yeah. So in the last page of this, there's references, and I can at least write down the references, so you can take a look at them. By the way, there's a beautiful paper by Legal called Ito's Extension Theory and Random Trees, where they also talk about the coalescence problem. And that appeared in this statistics or stochastic processing application. And there's another paper by Adrian Lambert, Coalescence Times for Branching Processes, and Annals of Applied Probability. And then Kirsting, Schweinsberg, and Wacholbinger, the evolving beta coalescent in an electronic general probability. And then there's a bunch of papers of mine. So the references are here.
Okay, we will find them.
All right, okay.
Okay, let's
Thank you.
thank Christian.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.